is a differentiable function. F of x, f of x, f of x, f of x is a differentiable function, so no problems. In other words, find an expression for the derivative of y. Find an expression of the derivative of y for each of the following functions. And we picked D. Perfect. We are looking at this expression, and what would you do first? Yes, because the denominator
is ugly.
Because the denominator is ugly, but because the denominator is very important. Let's go back. Because the denominator is one term. Otherwise you can't touch it. Because, thank you, because the denominator is one term. So I will have this, and I will simplify. How would you rewrite this? We did this before, about an hour ago. 1 over the square root of x can be replaced by
-1/2.
Careful. Yes. Good. Now careful here. X has power 1 and the square root of x has power 1/2. So I will copy the base, power 1 minus 1/2, and then times f of x. What power do I write? 1 minus 1/2.
1/2.
That's it. Now it's ready. Fully simplified. There is nothing else I can do here. And I can find y prime. Can anyone differentiate the first part? Because it's plus. And then we'll discuss the second part in a minute. Can anyone differentiate the first part?
-1/2 x to the -3/2.
Yes, -1/2 minus 1 is -3/2. Perfect, awesome, thank you very much. Now, we have to analyze the second part. What is it and what rule do we apply? We apply here. What is it and what rule applies here? Anyone?
Yeah, we're going to be applying the product rule here.
Awesome. Good. So let's differentiate the first part.
-1/2 x.
To which power?
-1/2.
That's it. Awesome. Times f of x plus x to 1/2 times
f of x.
careful. So 1 prime times 2 plus 1 times
F prime.
f prime. There is nothing we can do here. This can stay as is. This is it. Any questions on this problem? Any questions?
No.
Okay. Are we ready to move on?
Yes.
Okay. I'm just going to start. So this is page 8 and 9, so I'm moving on to 10 directly. Okay. Now, we can, as I promised in chapter 3, we can talk about L'Hopital Now we can. L'Hopital, that's his name. So it's L'Hopital's rule. What is it? So this mathematician showed that only for limits. So L'Hopital's rule is only for limits. From functions like f of x divided by g of x, as x approaches a, and only if the two indeterminate cases after the initial plug-in, only if we get 0 over 0 or infinity over infinity. So L'Hopital's rule requires limit of a function, and the two indeterminate cases that we obtain by initial plug-in are these. We do know infinity minus infinity. This does not work with L'Hopital unless we can change it into one or the other. So again, what are the conditions or hypotheses? First of all, limit. This is the first condition or hypothesis. And second condition is one or the other. Either this or this. If it's anything else, we need a lot of work to potentially change it into these two. But any other needs work. If it's not one or the other, we cannot apply L'Hopital's rule. And if it's not the limit. Okay? If you have a function and you differentiate or whatever, that's not L'Hopital's rule. Okay? So number one, condition is the limit, and number two, the condition is either 0 over 0 initial or infinity over infinity. The sign is not important. Yes?
Professor, I think we covered this when we were going over the limits, but negative infinity, it's all the same, right? Like
Yes, the sign doesn't matter. Yeah, the sign doesn't matter. So this mathematician showed that if we have a limit of a function and the initial is one or the other, then we can determine the limit as x approaches a from f of x divided by g of x by differentiating the top and differentiating the denominator. So let's stop for a moment, because this is very important, not to be confused with the quotient rule. So do not ever do this when you have a quotient, because you don't have a limit. And you don't have 0 over 0 or infinity over infinity, right? So this is specifically for a limit in which we have initial this or this, and for L'Hopital's rule. So he showed that if we have a limit, and we have these two, one or the other, then we can determine the limit like this. Notice that we are not applying the quotient rule here. He said, if both conditions are fulfilled, just differentiate the top and differentiate the denominator. So if we want to show and illustrate this, and let's say limit as x approaches infinity from x to the third plus 2x over e to the x plus 1, first of all, let's see where is the numerator going, because we need to make sure it's a limit, fine. But we need to see whether we have these two, one or the other. Where is the numerator going? Good. Where is the denominator going as x approaches infinity? Yes. So we say the following. I can apply L'Hopital's rule because I have a limit, and the initial indeterminate case is one or the other. Therefore, I will proceed to write this. What is the derivative of the numerator?
3x squared plus 2.
What is the derivative of the denominator?
E to the x.
Awesome. We continue. Where is the numerator going?
To infinity.
Where is the denominator going?
To infinity.
Good. I can apply L'Hopital's rule again because there is a limit and I have the initial infinity over infinity. So then, do not drop the limit operator. We did not apply it yet. What is the derivative of the numerator?
6x.
That's it. What is the derivative of the denominator?
E to the x.
Perfect. Again, where is the numerator going?
Infinity.
Where is the denominator going?
Infinity.
So then I can apply L'Hopital's rule again. What is the derivative of the top?
6.
What is the derivative of the denominator?
E to the x.
This is no longer an indeterminate case. The numerator approaches 6, the denominator approaches infinity. What is the answer now? And now I drop the limit operator. This is the last step when I apply the limit operator so I can drop it.
0.
Yes, 6 divided by huge approaches 0, which we know from here that y equals 0, horizontal asymptote at infinity. Okay? So this is an illustration. Now moving forward, we're not waiting till chapter 4. Moving forward, if you are given a limit, you can use L'Hopital's rule. As long as these two hypotheses are fulfilled. Otherwise, it's not applicable.
So, is there a proof for this, or how come L'Hopital's rule works?
There is a proof for this. I don't know if we have it in the book. Let me look at chapter 4 real quick, since you have a good question. L'Hopital's rule, I think it's before 4.5. I think it's in 4.4. And yes. Let me see. I can direct you to it if I don't know if we have a proof here of L'Hopital's rule. L'Hopital's rule. Yes, there is something. I don't know if it's a proof. There are some notes. No. If you want to look it up, you can. Yeah, there is sort of a proof on page 311, if you want to look at it.
Okay, thank you.
Excuse me.
Yes.
In what situations should we apply L'Hopital's rule? Like, would it be asked for specifically, or no?
This is an example. You're asked to find the limit of a function, and you have initial indeterminate case, either 0 over 0 or infinity over infinity.
Okay, thank you.
Because if you have a polynomial over a polynomial, maybe you don't need to do that. But if you have something like this with two different functions, an exponential and a polynomial, this is a much better or easier method to determine the limit. Now, if you have a polynomial that has a higher degree in the denominator, of course you will not do this because you can say, well, a higher degree in the denominator, the limit is 0. But here you're not 100% sure if x cubed or e to the x is bigger. Well, of course, e to the x is bigger. But you have to show step by step. So L'Hopital's rule is applicable for any limit that is kind of ambiguous. But it has to have these two, one or the other. Anything else? Very good questions. Anything else? Okay, so we're moving on to the derivatives of trig functions. So this is 3.3. So as you know, we have 6 trig functions and their inverses. But for now, we're going to look at just the functions. So we have sine x, cosine x, tangent x, cotangent x, secant x, and cosecant x. And yes, and their inverses. But for now, we're looking at these 6. But when we get to the inverses, we are going to mainly look at 3 of them. Okay, so like we did with e to the x, right? And we show that e to the x turns into e to the x. We can show any of the sine and cosine, sine prime, and cosine prime. I really wanted to put it outside. And cosine prime. So we can pick one or the other to show the proof, or if we don't want to show the proof, it's a little long, then I can just give you the results. And again, all these derivatives for these 6 functions, trig functions, they have to be added to the derivatives of the square root of x, the derivative of 1 over x, the derivative of, what else we looked at, e to the x. Okay, so, well, sine prime is cosine x, but cosine prime is negative sine x. Now, knowing these two, we can easily prove the other ones. So which one would you like to prove? You want to prove the tangent, you want to prove the cotangent, which one? Let's pick one.
Tangent.
Tangent. So we want to find the derivative of tangent, but we have to remember that the derivative, the function tangent can be replaced by?
Sine x, right?
Yes, indeed. What type of function is this, and what rule is applicable here?
It's division, so we would use the quotient.
Exactly, awesome. I always like to write cosine squared so I don't forget. I have to differentiate the top, and I get cosine, and times cosine, minus. I copy the top, and I differentiate the denominator, which is negative sine x. Let me write it one more time because it's not very clear over there. You don't have to copy it again. So now I will try to simplify it. And I see that cosine squared is here. And I see that negative sine x times negative sine x, that's why the parenthesis, negative sine x times negative sine x gives us what?
Plus sine squared x.
Anyone remembers the most important trig identity? Sine squared plus cosine squared to be, do not try to simplify
It's
this.
1.
Yes. So 1 over cosine squared. If the function starts with c, it's the opposite with s. So this is something that we need to add to our list. The square root of x, 1 over x, e to the x, sine and cosine. Now tangent prime is secant squared.
Why do we have the cosines times each other? I missed that.
Which one?
I thought it was the when we were actually writing out the quotient rule. I thought it was 1 times the other minus
So
1 times 2 minus 2 times 1.
So 1 prime times 2 minus 1 times 2 prime.
Right.
1 prime is cosine, then I have to copy the denominator. Then minus. I copy the numerator, but I have to differentiate the denominator. So then cosine times cosine is cosine squared, and negative sine x times negative sine x is positive sine squared. I'm not sure, did I explain this okay, or is it not clear?
No, you did. I looked down for just a split second and totally forgot what the derivatives for each were.
Oh, that's okay. And then sine squared plus cosine squared is 1, and 1 over cosine squared change it into secant squared. Is that okay now?
Yes. Thank
Okay, perfect. So let's write all of them, all 6. I'm on page 12. So sine x prime equals cosine x. Cosine x prime equals negative sine x. Tangent x prime equals secant squared x. Cotangent x prime equals negative cosecant squared x. Secant squared, cosecant squared, with minus. So now secant prime is secant times tangent. And cosecant prime is negative cosecant cotangent. So notice something very interesting. Tangent and secant are grouped together all the time. And cotangent and cosecant are together all the time. Tangent secant, secant secant tangent, cosecant cosecant cotangent, cotangent cosecant. So all the c's are alone together. I mean, they're in the same thing, same relationship, and then tangent with secant, and secant with secant tangent. Okay, so these are together and these are together.
So what about arcsine and arctangent?
We didn't get to those, to the inverse trig functions. We will. I
Got it.
promise. I promise we will not forget the inverse trig functions. They are in section 3.6. So in 3.6 we will look at sine inverse prime, cosine inverse prime, and tangent inverse prime. You know me, I don't like this notation. I prefer arc sine and arc cosine x and arc tangent x. I prefer these because these could be confusing. They shouldn't, but it happens that they are.